Now we go for tutorial for boundary layer. Number 3 here. Transition from laminar to turbulent boundary layer flow actually occurs over a finite length of the surface. Transition is the duration which the velocity profile and wall shear stress adjust from laminar to turbulent forms. A useful approximation during transition is that the momentum thickness of the boundary layer remains constant. Assuming constant momentum thickness, find the ratio of delta turbulent over delta laminar from transition from a parabolic laminar velocity profile to a 1/7 power law turbulent velocity profile. So in this question, they try to uh, tricks you with the question. So if you read the question very well, I think you could answer the question. First, it tricks you that the momentum thickness of the boundary layer remain constant. So this is the main, the important tricks in this question. So it's talking about the transition and so on. And from this situation, normally researcher will take this consideration. So we assume that momentum thickness for boundary layer is remain constant. So it can be said like this. So we have a laminar and then it turns into turbulent. So at this transition, at the critical point here, so the value of momentum thickness, so means the value of theta here is constant. So what is the meaning of constant here? So means that the value of momentum thickness, if you calculate in laminar condition, will be same with the value that the value of theta if you calculate using turbulent boundary layer equation. So means that both condition, laminar and turbulent, will give you same amount. Okay. So and then the question is, find the ratio of delta turbulent over delta laminar from transition for a parabolic laminar velocity profile to 1/7 power turbulent velocity profile. So here again you need to familiar with common terms in boundary layer. For parabolic laminar means we assume that velocity profile at laminar here is u over u with parabolic, means with power of 2. So, and then at the turbulent here is 1/7 power law turbulent velocity profile, means the velocity profile here is u over u is equal 1 over delta by the power of 1 over 7. So 1/7 power law is this one. So means now you know the velocity profile, then you could solve this problem. Okay, so the idea is to find the ratio of delta turbulent and delta laminar, but the subset or the main point is the value of theta is constant. So what we could do is, okay, so this is I just show this in terms of eta. Okay, I hope you could make some practice to solve problem in eta. It is okay for you to solve this by using u over u, because in our tutorial I already show you both method by using u over u, y per delta with eta. Okay, let's say this is the theta for laminar, and then if you substitute the value of eta here, okay, you will get 2 over 15 delta. Okay, here just to differentiate between calculation in laminar and calculation in turbulent, so I put delta laminar here. So you could, you also could solve this problem by using the common theta is equal u over u 1 minus u over u dy here. Okay, okay, so you could solve by this one. Okay, please try this at home. So, and then this is the value 2 over 15 delta laminar. And then if we use 1/7 power law, so momentum thickness turbulent will give a 7 over 72 delta turbulent. So, and then what we need to do is we need to define what is value of delta turbulent over delta laminar. So what we do here is we know that delta turbulent and over delta lamina can be calculated like this. So the ratio is equal 1.37. So where we could get this number, okay, you could see here. Okay, so we have the delta lamina is equal of this one, and the theta turbulent is equal of this one. And then from the condition given in the question, the momentum thickness is constant. So now we equalize these two values. So we have at first 2 over 15 delta lamina is equal to 7 over 72 delta turbulent. Then you could rearrange this equation into this term, and finally you could calculate the ratio of delta turbulent over delta lamina.